Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will talk about reservoir allocation in MBAL software. All right, so we are now inside the MBAL. We go to tool. Now instead of selecting material balance, we will select reservoir allocation. Okay, go to reservoir allocation. All right, and now you can follow me. We go to the options. Okay, reservoir fluid oil, track impurities, no. And for the user information, you can type in the company, field, location, platform, and also user comments. We click done. All right. Now you can see one tank, but it is still blank. Now we go to PVT and we select fluid properties. All right. Now we need to input informations for this PVT data oil window. All right, so you can follow me. Formation GOR 650, standard cubic feet per stock tank barrel, oil gravity 40. But please be careful here. The unit is kilogram per meter cube. I will change it to API. All right, oil gravity. But be careful here. The unit is in kilogram per meter cube. So I will change it first to API. Click done. Go to units. All right, so let's find API or gravity, the oil gravity. This one, oil gravity. You can see the input unit selections in kilogram per meter cubic. We change it to API. Oil production in mmstb, million stock tank barrel. Okay, I use that. Click OK. Go back to PVT. Fluid properties. All right, so for oil gravity is 40 API. Gas gravity 0.6. No H2S, no CO2, no nitrogen, and for water salinity, 25,000 ppm. If you have data, you can do matching by inputting the laboratory data here and click match. But I will skip this matching now for this video. Cancel. And for the correlations, I use Glasso for bubble point pressure, solution GOR, and oil formation volume factor. For oil viscosity, as usual, I prefer Bill et al. But of course, if you have laboratory data, real data, you can do matching and select the best correlation. All right. For separator, single stage separator. And I will have 3 reservoirs actually in this example, but I only have one PVT data. Okay, the PVT data is PVT01 here. So click validate. Okay, we are validated. Click done. All right, now we have this tank. We can go to input, tank data. All right, you can follow me for this first tank. Tank type oil, the temperature 210. Initial reservoir pressure 2725.3. Porosity 0.25. Connaught water saturation 0.05. Water compressibility, I have the data. So instead of using correlation, I will input 3 times 10 to the power of -6. All right. Gas cap, no gas cap with original oil in place of 20 mmstb and start of production 1st January of 2000. PVT definition, I will use this one, PVT1, and I can calculate the bubble point pressure. Press calc. I get the bubble point pressure. Click done. All right. Now, suppose I already know the water influx, the aquifer parameters. So I go to water influx. I change it to this model, Hurst van Everdingen modified method. Or instead, I will use Hurst and van Everdingen and Dake with the system radial aquifer For example, I already know the reservoir thickness, the reservoir radius, in even aquifer permeability. So I will input the information for the aquifer here. All right, so the reservoir thickness 100 feet with radius of this one with outer inner radius ratio of 4 and the aquifer permeability quite high, 200,000. All right, millidarcies. Okay, so far so good. For the rock compressibility, I will use user specified and the number is this one, 4 times 10 to the power of minus 6. Okay, rock compaction, relative permeability, we will use Corey functions. You can follow me for this table, residual saturation fraction. Okay, the endpoint, exponent 1, and the KRO. Okay, and then for this one, 0.82, and for the gas relative permeability with endpoint, okay, exponent 2. All right, you can check the plot by clicking this one. Okay, KRO versus water saturation, or KRW versus water saturation, KRO, oil relative permeability versus saturation of oil, and the KRG versus saturation of gas. Okay, close. Now for the production history, I will leave it blank, all right, because I will do reservoir allocation. So I have the production history from a particular well, from one well, and I will allocate the production history to each tank, to each reservoir. All right, so we can skip this one, production history, click done. Okay, error, cannot water saturation from the tank parameter data page, this one, is greater than that in the relative permeability data page. This is not possible, so either click OK to copy it to the relative permeability data page, or click cancel to correct the problem. So I will correct the problem. This one, Connaught water saturation. Okay, I will check it back for the relative permeability. Okay, this one. Okay, 0.05. This one. Okay, done. All right. So I have one tank, I have one reservoir. I will move it there. Or we can go to input, tank data. Oh, here. We can add new tank by clicking this one. All right, so I now have tank 2. I will first click done. Okay, I have this one, tank 2. I will move it there. All right, uncheck the move. Go back to input, or we will go to this tank. All right, so for the second tank, for the second reservoir, you can follow me again. Tank type, oil, temperature 210, initial reservoir pressure to 5.3 with porosity 0.25, Connaught water saturation. Okay, water compressibility same, gas cap downhole ratio 0, the original oil in place 30 million stock tank barrel of oil, the same starting of the production. Okay, calculate the bubble point pressure, this one, click done. Water influx, we will do the same steps. Okay, encroachment angle 140 degrees, and the aquifer permeability the same. I will click done first. I will check the encroachment angle for the first tank, making sure that I have the right number. This should be 140. Click done. Again, go back to tank 2, raw compressibility, user specified. All right. Raw compaction, relative permeability data. All right. 0.05, endpoint 0.9, exponent 1. This one 0.15, 0.82, okay, 0.952. All right. Again, we can skip the production history. The production from a well, production data, production history from my well will be distributed, will be allocated to each tank, including tank 2. Okay. And then we can go to the third tank, click done. All right. Or go back to tank 2 and add one tank, tank 3. All right, click done, or we can input the data now. Actually, the values are the same. So yeah, they're actually the same, except the original oil in place. Okay, 3E minus 6, 0, original oil in place. This one, the third tank, has the highest OIP, original oil in place, of 50 million octane barrel. Start of production, okay, 2000. Calculate bubble point pressure, the same value. Water influx, this one, okay, 100. Outer inner radius ratio, 4, 140 for the encroachment angle, 200,000 millidarcies for the aquifer permeability. For the raw compressibility, user specified, this one, okay. Raw compaction, relative permeability, I will copy the table from tank 2, okay, copy table, done. Go back to third tank, paste the table. All right, very easy. Again, we will skip the production history. Click done. I will move the third tank there. All right, so we have completed the third tank. We constructed the 3 reservoir models, tank 1, tank 2, and tank 3. All right, they have the same characteristics. They have the same properties except the original oil in place. This one, the smallest, 20 million stock tank barrel. This one, 30. And this one, the biggest, 50. All right, so they will produce oil to one particular well. So I will add well here. Okay. Or I can go to input, wells data. All right, click this one. Okay, so now I create well type oil producer, producing from tank 1, tank 2, and tank 3. Okay, let's check. Click done. All right, this one, this well, I will move the well there. Okay, interesting. All right, so this well will produce oil. We have the production history data from this well. And actually this well will get the oil from these three reservoirs, tank 1, tank 2, and tank 3. But we don't have, or we don't know the production allocation or the production contribution from each tank. So we will calculate the production allocation by first inputting the data in well 1. Okay, so let's go, double click. So we are now inside the well input data. Here we go to production history. Now I will copy my data, my production history data from my spreadsheet and paste the data here. Okay, I've copied my data, right click, paste table. All right, so this is the production history obtained from this well. I have the time, reservoir pressure, cumulative oil produced in million stock tank barrel, cumulative gas produced in million standard cubic feet, and cumulative water produced in million stock tank barrel. All right, let's check the plot. Okay, this one, well, remove all first, select the well, reservoir pressure, okay, cumulative oil production, okay, remove all, cumulative gas production, and cumulative water production, the red line. Okay, what about cumulative GOR? This one. Okay, so far so good. Close. Now inflow performance. So actually we will distribute, or we will allocate the production based on this one, based on the inflow performance from each reservoir. Okay, so let's be careful here. We first go to tank 1. All right, so this is the information sheet for tank 1. Well type oil producer, inflow performance. All right, we will use straight line first, above bubble point pressure, and then Fogel below the bubble point pressure. So select this one. Fractional flow model, we'll use tank. Okay. Productivity index, 5. Stock tank barrel per day per PSI. Cross flow injectivity index, keep it as it is. You can see the note. Cross flow injectivity index is only used if cross flow occurs between layers. Okay. And then for the test water cut 0, no gravel pack. IPR pressure drop shift, no, 0. Permeability correction, no. Okay. Production schedule, we can leave it blank. Click done. Validate. Okay. Now for the second tank, the same. The rest of the data input are the same, except this one, productivity index. The second tank will have productivity index of 3, lower than the first tank. And again, for the third tank, it will have productivity index of 2. All right, now we can validate. Okay, very easy. And then we can create the plot. Okay. Or we need to first check it again. No need to match the IPR. Okay. Click done first. Go back again. The plot. Okay. Please be careful here. Something's not right. Oh yeah, I see. We cannot create the plot because we don't know the pressure distribution, pressure profile in each tank. All right, because we haven't run the production allocation. So actually we cannot run the IPR. We cannot construct the IPR first. So instead of creating the IPR now, we can click done. All right. we can go to calculate, check the setup. Okay, allocation step size, automatic, recommended, done. Now we can click run allocation. Check again first. No production history. All right. No production history. Third tank, no production history. Now, after I click the run allocation button, we'll have production history in each reservoir, in each layer, or in each tank. Okay, let's go to the run allocation. Here, the run allocation window, click calculate. Please be careful here. The initial pressure from tank 1 cannot be less than the bubble point pressure calculated at the tank temperature. All right, please check your PVT. Yeah, I know this will happen. You can see here we have gas cap downhole ratio of 0. All right, but actually our initial reservoir pressure is below the bubble point pressure. This is not right. If our reservoir pressure is below the bubble point pressure, we will have gas cap. All right, we will have gas cap because the reservoir pressure, initial reservoir pressure, is lower than the bubble point pressure. So basically the gas will bubble up and we will have gas cap. So I will correct the initial reservoir pressure, or I will check the PVT data. All right, let's go back to PVT data first. All right, fluid properties. I skipped the match data. Oh yeah, but I skipped this table, I think. There. All right. Actually, we have this table. We have this data. So I've copied my data and I will paste it here. All right, so the temperature is 210 and the bubble point pressure is this one. This is the bubble point pressure and the initial reservoir pressure. So at this condition, we can have zero gas cap. All right, we can have zero gas cap downhole ratio because the initial reservoir pressure is still the same with bubble point pressure. Okay, if your initial reservoir pressure is below the bubble point pressure, the gas will bubble up and you will have gas cap. All right, the reservoir will be in saturated condition. But if you have initial reservoir pressure that is higher than the bubble point pressure, will be undersaturated. All right, the condition of the reservoir will be undersaturated. But if the initial reservoir pressure is equal to the bubble point pressure, then we can say it is still undersaturated. And at undersaturated condition, we can have no gas cap. Okay, and we have this data: reservoir pressure, gas oil ratio, oil viscosity or oil formation volume factor, and also gas formation volume factor. We can plot at temperature of 210 the pressure. The bubble point pressure will be constant. Gas oil ratio, remove all first. Oil formation volume factor. All right, at bubble point pressure, the value will be highest and then it will decline. Gas formation volume factor. Okay, so far so good. We can close. Done. Click done. We will check the tank 1. All right, now the bubble point is correct already, 2725.3. Okay, tank 2. All right, so far so good. So usually as an engineer, you will have this same problem in your daily job, doing MBAL simulation or other analysis. Calculate PB. All right, so now we can go back to calculate and run allocation. Calculate. All right. You can see we have the time, we have the reservoir average reservoir pressure, cumulative oil produced, cumulative gas produced, cumulative water produced, and the calculated oil rate, gas rate, water rate. We can create the plot. Tank 1, let's see the tank pressure profile. Okay. Tank 2, all right. Tank 3, interesting. All right, so the tank 1 will have the pressure decline faster compared to tank 2 and then tank 3. Tank 3 will show the slowest reservoir pressure decline. You can see because the size of the oil price, the size of the reservoir, or you can see from the initial oil in place, all right? Oil initially in place. Tank 1 will have the smallest OIP, oil initially in place. That's why we can say it will be smaller in size, and of course the reservoir pressure will decline faster compared to the third tank or second tank. Okay, remove all. Cumulative oil production, tank 1, tank 2, tank 1. All right, remove all. Tank 1, oil rate. Tank 2, oil rate. Tank 3, oil rate. Yeah, of course, the oil rate in tank 1 will decline faster again compared to tank 2 and tank 3. All right, because of the same reason, because tank 1 is the smallest and then followed by the second tank and the third tank. Okay. Tank 1, gas rate. Tank 2, gas rate. Tank 3, gas rate. Okay. Because the gas rate will be calculated from the GOR. All right. We have numbers from oil rate. We have values from oil rate. And we also have GOR, right? Tank 1, water cut from 0 to 75, all right, in about 11 years. Tank 2, water cut. The water cut will rise slower compared to the tank 1. Tank 3, all right, the water cut increase show the lowest rate compared to tank 1 and tank 2. Again, you can do the plotting, the same plotting technique for other parameters. Okay, so far so good. So we can say that our production allocation is successful. Okay. Again, cumulative oil production from tank 1, or remove all first. Tank 1, cumulative oil production. Tank 2, cumulative oil production. Tank 3, cumulative oil production. Why we will get the cumulative oil production highest from tank 1? You can see because, again, the productivity index from the tank 1 is the highest compared to second tank and third tank. And that is also why that we will have oil decline faster in tank 1. First, because the size of the reservoir is, of course, smaller for tank 1, but also because the production rate resulting from the higher productivity index, the production rate is also higher. All right, here, the production rate higher. That's why it will decline faster because, or I mean, this is for the third tank. The first tank, here you can see, because the productivity index from the first tank is the highest, but the size, the in place is the lowest, then first tank will show the fastest production decline and fastest reservoir pressure decline. All right, click close. So far so good. Lastly, I will show you the IPR. Well, one. Now, hopefully we can create the plot for the IPR. All right. Now we have the flowing bottom hole pressure data. We have the pressure information. Okay. I mean, I don't mean that we have this flowing bottom hole pressure data, but we have reservoir pressure data actually. Okay. The red line comes from tank 1, the biggest IPR or the highest productivity index. The green line, tank 2, and the lowest productivity index is from tank 3. And if you combine all the IPRs from the tanks, you will get the black line. All right. And we also now have the AOF, or absolute open flow or maximum flow rate, for each tank and for the combination. All right. I think we can call it a day. So in this video, we have learned about reservoir allocation. We constructed 3 reservoirs producing oil to one particular well. We have production history for the well, and then the production history from the well will be allocated to each reservoir based on their parameters, and also of course based on their productivity index. All right, and then we run the production allocation calculation and we get the production history from each reservoir, and then we can create the IPR for each reservoir. All right, so that's all. I hope you enjoyed the video. I hope this video is useful. Thank you so much for watching, and see you again in the next MBAL videos. Thank you.